Here we're doing proof 7.1, and what we're going to be proving is that each vector that has a right inverse, that inverse is also its left inverse, and that the right identity is also left identity, and that vector addition is commutative. So first, we're going to prove that this is equal to 0, given that vector v plus the inverse is equal to 0. So to prove this, we're gonna say that there exists a vector w such that the inverse plus w is equal to 0. So we're gonna first start with this and then equal it to itself, which is, as Paul would say, pretty trivial. And then, since vector addition is associative, we can group these two together and then these together. Now, this from this is equal to 0, so we bring this down, is equal to, and then we were given that this is equal to 0, so we haven't used this fact, which is very tricky. We add w, and then we get this is equal to this. Since we started with this is equal to 0, we have proved that the right is also equal to the left inverse, and part 1 is done. Part 2, proving that the right is equal to the left identity. So first we start with these vectors, and then since we already proved that 0 is equal to v plus its inverse, we could plug that in from part 1, and then we're gonna say that since vector addition is associative again, we're gonna group these vectors together. And since we proved in above that this is also equal to 0, we get v plus 0 is equal to v. And thus we also proved that the right is equal to the left identity. The third part is proving that addition is commutative. So trivially, we first start out with equating, this is a plus, something equal to itself. But we applied the distributive law a little bit differently. So on this side we have 1 times this plus the same. Over here we do it a little bit different. And then we take all the variables out. The whole point of doing the distributive law a little bit differently is so that you get the orders a little bit different, so that you end up proving what you want to prove. So that was pretty straightforward. And then by multiplicative identity, we get v plus w plus w, v plus w is equal to v plus w plus w. We add negative v and subtract w from both sides, so we do something like this. Subtract w, subtract w. We group these together by just vector addition again. Underline there. There you go. And then we proved in part 1 that this is equal to 0. So we bring those terms down. This is just all coming from the first part of the proof. And then the 0 plus w is basically w because from part 2. So we get w plus v is equal to v plus w. And we prove that vector addition is commutative. Yay!